that goes along with stars being born and all that, and that's more like chapter 13, chapter 14. So I think that's probably what we'll be doing next week at some point. But chapter 11 is a good one, and I wanted to make sure the lights were nice and dim, because when we're talking about stars, which is what we're talking about, it helps to, in fact, I probably will just turn off all the lights, because you can't see those little faint stars as well. So in the textbook, up to now, we've been kind of a mixture of photographs and figures and all that, but now we're kind of going to do more like photographs. So this actually is a photograph of stars. I don't know if you see the constellation Orion in there. Orion actually, this is where Orion is standing up, right? Here is actually kind of his shoulders, and here is kind of the knees of his toga, okay? But Orion is usually on the horizon kind of laying down. So the other thing about Orion is he actually is wearing a toga that has a belt at his waist. And so those three stars, those are more like, I don't say, perpendicular to the horizon. Actually, those belt stars are really kind of characteristic. The cool thing about Orion is actually he also has a sword. This is the sword.
I totally don't see it.
You don't see it? We'll have to pull up Orion. But yeah, so this is his, kind of have, and this is his knees go down here, and his shoulders are here, and his head's here. I don't know if that helps. Okay.
Yeah, I didn't know where his head was.
Okay, good. Yeah. In here, we have talked about nebula a lot or whatever, and actually, I don't know if you can see a little bit of what we call nebulosity right there. Okay, and actually, even through binoculars, you can get a sense for. That actually is what we call the Orion Nebula, and it's Messier object number 42. So M42 is right there. Looks like we have a little bit of nebulosity there too, don't we? But anyway, chapter 12 is kind of, before we talk about the lives of stars, we kind of need to talk about how we describe stars. So an important thing about describing a star is like how bright it is, okay? And actually, there's different ways to think about its brightness. There's the way I call where you visit the star and have your little light meter, and you come up with what we call its luminosity. Okay, now the problem with stars, and we're going to have to address this, is stars are not on all the same distance from us. Okay, so if we were to visit it and put a little light meter, we would come up with the wattage of the star. That's called its luminosity. How bright a star appears is called its apparent brightness. Sometimes apparent brightness is synonymous with just brightness. So if you hear brightness, that's the same thing as apparent brightness. Okay? Brightness, apparent brightness. Now, in astronomy, just like in chemistry, we have a little m, and this is a little m, and we actually have a capital M coming up. So we have a little m and a big M. Apparent brightness, how it appears, and that's kind of how this figure is. So how our sun appears is kind of a function of how much light, the luminosity of the sun, and it's also a function of how far away the sun is. Okay, it's the same thing with any star. How bright does a star appear? Well, how much energy is it pumping out, and how far away is it from us? Because, like, if I were to, let's just do a car. What if we had a car that was like, just out parking right here, okay, the car right there. And it was shining both its headlights at us. We take that same car, and if we put it twice as far, it's shining the same pair of headlights, it's going to look dimmer. We can take that same car and go 3 times as far, and it's going to look dimmer. The thing about energy, including light energy, is that it basically becomes diluted the farther away it is. And it's called the inverse square law. So this is actually talking about the inverse square law. So basically, we have our source in here, which could be a light, could be a pair of headlights, okay, shining in all directions. If you are at a distance, this first distance within this purple sphere, it's going to have a certain apparent brightness. If you instead crank it up and you go this far away, the light's going to be diluted. Not diluted, diluted, okay? And then if you crank it up and go this far away, okay, it's going to be diluted even further. The light diminishes by what we call the square of the distance. So I'll go ahead and the distance, I'll make it R. and r squared. Inverse square law. Okay. So we have a little bit of a trick with stars. Okay, so not only, as you might imagine, stars are not all created equal, and that's part of what this chapter is going to talk about. Not only do we have stars that have different luminosities, they have different energy ratings, but we also have stars that are different distances from us. Okay, so just because a star is dim, it could be one of two things. It could mean it has a low luminosity, or it could mean it's far away from us. Okay. And we're going to kind of fix that or normalize that here in a minute. So remember, brightness is apparent brightness. Brightness is what it appears, okay? Brightness is apparent brightness. Luminosity is if you visit the star and what it's pumping out. So here's the deal, and distance, of course, is between the distance between us and the star. Here we have a little equation, okay? We basically have three variables, three unknowns. We have brightness, luminosity, the energy the star is pumping out, and distance to the star. One of the things you know about, like if you have three variables like that in one equation, if you know two of those variables, you can find the other thing. So if we wanted to know how bright a star would appear, if we take its luminosity divided by its distance squared from us, then we can knock out how bright the apparent brightness. Well, we can rearrange that, and if instead we wanted to know its luminosity. Now, luminosity is you visit the star, you have your little light meter, you say how many watts of light it's putting out. So if we wanted to know the luminosity, we could take the apparent brightness, and if we knew the distance, and we'll kind of talk about how you get distance, we could knock out its luminosity if we know the brightness and the distance. The last thing we could solve for is the distance. So here we go. If we take that same thing and solve for distance, as you know, since distance is squared, we're going to have to take the square root of something, right? So actually, we can knock out the distance if we take the square root of how bright it appears. Sorry, if we take the square root of how much energy it's pumping out divided by 4 pi and how bright it appears. So it's just kind of ways we can kind of manipulate those three variables. All right. Well, one way to get distance actually is from parallax. Parallax, earlier in the course, was where I said if you put your finger in front of your nose and close one eye and close another eye, your finger looks like it moves against the background. The deal there is your finger is pretty close to you, and by closing one eye and another eye, you're kind of changing your reference point, okay? So it looks different. Now, if you take your finger and move it farther from you and close one eye and close the other eye, okay, it doesn't move as much. The farther you move your finger from you and close one eye than the other eye, it moves less, okay? So actually, and I think we looked at this before, one of the arguments for the whole putting the sun in the center of our solar system, here's our sun obviously, okay? One of the problems with putting the sun there is we said, hey dude, you know, 6 months apart, January and July, if something's kind of close to you, like your finger, you're going to actually see that star kind of jump against the background stars. And that's actually what we do see. Okay, so the purple is the star of interest, relative to that of your finger, okay? And kind of closing one eye and the other eye, that's moving 6 months apart. And we do see some wiggle, okay, using astrometric data, okay, to the location of that star against the background stars. Now, it's just kind of like your finger, though, that the farther, if we take this and move it farther away, we're going to see less wiggle the farther away the star is. Kind of take that to the end point where basically you can have the star, if you have the star, and I have it up here in a minute, if you have the star that is, remember light year is the distance that, light year is a long ways away. If you take a star and locate it 1,500 light years away, okay, and try to see its movement against the background stars, you will not see it. Okay, it's going to be too far. But bottom line is you can use, and it ends up being an angle, you can use the amount of wiggle and knock out the distance. That's my point here. We're going to look at other ways you can determine distances to objects, but that's one way. And it does have a limitation. Okay, so you see kind of the assortment of colors there, hopefully. I don't know, if you're colorblind, it might make it a little more challenging. I see green and orange and red and blue. No, blue, more green. So, but one of the things I want to say with regard to the characteristic of luminosity. Now, we compare other stars to the sun, makes sense. So anytime you see the subscript sun, that means of the sun. So L of the sun means the luminosity of the sun. So we kind of have a range of luminosities with regard to stars. Now again, this is visiting the star and having your little light meter and saying how many watts of light it's putting out. Okay, so the most luminous are 10 to the 6th times the luminosity of our sun. Now I just want to remind you, I think we did the other day, but if you have something packed up in scientific notation, what that means is 1, 0, 0, 0, 0, 0, 0, 0, 0, times the luminosity of our sun. So that's a big number. Okay. On the low end, here we go. Packed up in scientific notation, that would be actually, okay, that is 1 times 10 to the negative 4th. So that's quite the fraction of the luminosity of our sun. So one of the things that's cool in kind of this chapter on stars is you're like, oh my gosh, stars are definitely not created equal. We know that because they're different colors. They're definitely not created equal because they have different luminosity values. So what is that? Okay, so little m is brightness or apparent brightness. So here's one for you. So I like to think back in the years, 190, 120 BC. I like to think of Hipparchus basically finding a nice dark sky in Greece and laying down and looking up at the stars. And he basically said that the brightest star that he saw, the brightest star, not the planet, but the brightest star he saw was a +1, which actually now I think about it, that's pretty dim. The brightest star he saw was a +1. Now I'm going to warn you, this scale seems a little backwards. The dimmest star he saw was a +6. You already see where it seems backward? So there'll be a multiple choice question, at least one that kind of says, do you kind of understand that +1 is brighter than +6? And actually we kept that same scale now. But we had to build on it because honestly, we know things that are brighter than a +6 and we know things that are dimmer than, we know things that are brighter than a +1, things that are dimmer than a +6. But we did keep it. The other thing to keep in mind is that as you jump from 1 to 2, actually a +1 to a +2, you are going down by a factor of 10. Okay, so it's actually a base 10 sort of scale. So like I said, we see things that are brighter than 1, and if they're brighter than 1, they have to go on the, they have to basically go down to the, through 0 to the negative numbers.
This is dimmer. I just want to make sure. Is that
Stars that are dimmer.
right? Or should I be bright?
No, that should be brighter.
Okay.
Thank you.
Yeah.
Thanks. Okay. Yeah, this should be brighter. Good job, Adam. For stars that are brighter than 0, we need to use negative numbers. So one of the things that some people, including me, like to kind of keep up with is the International Space Station. It's a long story. The International Space Station orbits the Earth. And there are times that actually we can see the International Space Station, okay, make a pass. It makes a pass every 90 minutes, every hour and a half. Now, the deal, though, is you're not really seeing the International Space Station. What you're seeing, actually, is basically it's got solar panels, so you're seeing kind of the glint from the solar panels. But the thing is, they always give you an apparent magnitude value. So, like, if it says -3.5, you're like, oh, my gosh, it's so worth trying to find that or to watch that pass. If they say it's got a pass that's a value of, +3, you're like, I don't think so. Okay, so the more negative, the more exciting it is. So those black and white sky maps that I've been giving you, and I'll give you again one for November, actually they have magnitude scale on them. And that's what they're dealing, that's the lowercase m, the apparent magnitude. So let's just look at some objects, okay, so that weren't included in Hipparchus scale. So the sun, pretty darn bright. It actually is an apparent magnitude of negative 26.7. Let's see, what else we got? Full moon, pretty bright, negative 12.6. Venus, pretty darn bright right now, negative 4.4. Sirius, now we looked at Orion a minute ago, the constellation Orion, which again is kind of tilted actually on the horizon more than you saw it kind of straight up and down. But Orion, the great warrior, actually has a dog, and it's called Canis Major, big dog. And the brightest star in Canis Major, actually the brightest star we can see in the northern hemisphere, is Sirius, seriously. And it's a negative 1.4. So just on dark skies, having optimum conditions, like no glow from a city or anything, the naked eye for most people can see about a magnitude of +6. That's what Hipparchus saw, right? If you have binoculars, it gathers light. You can actually up that to a +10. Pluto, though, you're not going to see with binoculars because it's dimmer. It's a +15. The Hubble Space Telescope can actually give us information and image objects that are a +30.
What's your telescope go to?
What's that?
What's your telescope go to?
I don't know. Not that much. That's a good question. So here is the capital M I was talking about. And it also deals with brightness of a star, but actually it's called absolute magnitude. Now, in order to make sense out of stars, how bright stars appear, what would work well is if we could take all the stars and put them at the same distance from us. And that's actually what this scale does. It actually kind of, in my own mind, I think of taking all the stars and this, or whatever, and lining it up. That is actually a distance of 10 parsecs from us. And I've talked about a light year, but not a parsec this semester. But a parsec is related to a light year this way. So 1 parsec, which is just a distance, is 3.26 light years. So 10 parsecs, you're talking about 32.6 light years away. Okay? So basically line up everything and then take one last look at it, and however bright it is, that's its absolute magnitude. So it's like in a process in science, we call that normalizing. It's taking the effective distance away. Okay? That's pretty cool. So for example, we said the sun was a negative 26. Okay? We said the sun is like a negative 26 apparent magnitude. If you were to take the sun, and I don't advise this, but if you were to take the sun and move it instead of 1 AU away from the Earth, if you were to move it 32.6 light years from the Earth, that would be bad, right? But then if you were to look back at it, it would have it would look dimmer, okay? It would actually, on the apparent magnitude scale, it would be a +4.9, okay? So you can still see it, and so just that very fact, okay, makes it actually +4.9 is its absolute magnitude, +4.9. I didn't think about this till just now. I've been teaching this all this time, but actually we're going to see the sun kind of mixed with other stars, and you're going to see that its absolute magnitude is +4.9. Okay, we need to not treat it any differently than we treat other stars. So with regard to stars, speaking of, if you go ahead and kind of level the playing field, put them all same distance from us, then you're looking at absolute magnitudes ranging from -10, which is really bright, to a +17. Okay, again, this is removing the effective distance, basically. Okay, so since we're removing the effective distance, actually this absolute magnitude, and this is important, the absolute magnitude actually gives us the same information as visiting the star. So the absolute magnitude gives us the same information as relative luminosity. Road trip. So with regard to the color of a star, and I think we kind of talked about this earlier in the class, the color a star emits, actually the color anything emits, if it's glowing from thermal energy or glowing from radiation, the color it emits is an indication of its temperature. So down here, actually, you see these radiation curves of 4 different objects. We had this in an earlier chapter. The hottest object is right here, okay? The surface of that star, and when we talk about stars, you're going to know that the core of the stars are a lot hotter, but the surface of that star in the Kelvin scale is 15,000 Kelvin, okay? A few things about that first curve. Notice that it is pretty darn high, okay? And it's also skewed over here to the shorter wavelength. Remember, this is shorter, along the x-axis is wavelength. We have shorter wavelength, longer wavelength, and then shorter wavelength is more energy, more E, and longer wavelength is less energy. So this all makes sense. Like then, for instance, if we go to the other extreme, okay, we have another star, that's the red line there. Okay, notice it's squattier, and it's shifted over there. Our sun, actually, we just recently talked about how hot is the surface of our sun, and it's about 6,000 Kelvin, 5,800 Kelvin, and that's that middle line. And then this, I get a kick out of this one down here. This kind of hides from me. But you see that little black line? That actually, human beings, basically, if you were to gather the information that human beings emit, this is kind of where that falls, related to its temperature. So bottom line is blue stars are hottest, red stars are coolest. Well, we're going to piggyback on that in this chapter. Okay, so when we go to characterize stars, an important information about a star actually is what we call its spectral type. So here we have 7 spectral types. Spectral types. It is arranged by increasing temperatures. So this O type we would think would be blue, and you're right. This M type you think would be red, and you're right. It's just basically consistent with all we've been talking about. But an important way to categorize a star is its spectral type. And it seems kind of scrambled because you're like, dude, why didn't you just go A is the hottest, you know, and then whatever, you know, A, B, C, D, E, F, G. Well, it didn't work out that way, and I'm going to kind of tell you, I think, in a minute why. But to unscramble then in order of hottest to coolest, there's a mnemonic device called, oh, be a fine guy or girl, kiss me. And in that case, each letter represents a spectral type. So O is the hottest. The hottest spectral type, and M is the coolest. Because when we're classifying stars, it's important, that whole surface temperature is very important. Let's see, what else do we have? Over here, I don't know if you remember, again, something we talked about earlier in the class. Do you remember? Let me pick out a good one. Let's go to the F type. I'll go in F and G. Do those look like absorption line spectra? Or basically electrons are absorbing a certain amount of light at those particular wavelengths. That's what these are. These are things we've already talked about. When we talked about them before, we said you can use them like a kind of a DNA sort of thing. You can look at a library and understand what elements there are based upon where that line is. So these are spectra from stars. So let me go ahead and circle the sun, because I like what this does. It kind of gives some examples. So the sun is actually a G-type star. Pretty cool. So the sun is a G-type star. It's kind of the middle of the road. Oh, be a fine guy, kiss me. With regard to surface temperatures, the hottest stars tend to be pushing 50,000 Kelvin. The coolest stars are about 3,000 Kelvin compared to the sun's 5,800 Kelvin. Okay, so this is the same figure you saw a minute ago. Again, you're going to want to kind of get a sense for these 7 spectral types, where O is the hottest and M is the coolest. The second column gives examples. The third column gives surface temperatures. Okay. Now, one thing I want to kind of talk you through a little bit is, do you see, and it took them a little while to figure this out, but do you see up here that especially beginning with maybe the A, as you get hotter right here, the A type, the B type, the O type, you'll be like, where are the lines? Where are the spectral lines? And that was one of the things they had to kind of consider. Well, before I show you kind of the answer over here, what's creating those spectral lines, I think this was a question on your exam, is it's the electrons create these spectral lines. Electrons create the lines. So here we go. All right, now, one of the things I think we've kind of hit on here a little bit in this class is the whole thing about temperature and matter. And we said that all matter has motion. We said if you take matter and you cool it down, it slows down. Remember that? Okay. If you take matter and you heat it up, it gets more kinetic energy, which is all cool. This is actually kind of talking about that. So down here we have the coldest temperature on listed 10 Kelvin. 10 Kelvin. That's cool. Okay. At 10 Kelvin, and we're kind of, I think your author kind of just uses water. At 10 Kelvin, you would think water would be a solid, and you're right. Okay. Now, one of the things about that is that I want to kind of not emphasize its motion as much. It wouldn't have much kinetic energy, right? But the other thing is, can you kind of see those little, it looks like six-sided figures, which is correct. Snowflakes definitely have that hexagon going for them. But those little lines right there, those are like intermolecular bonds. They're just all stuck together, really bonded. Now, the point of this slide is we warm it up, okay? 10 to the second power is 100, right? So here we have 100 Kelvin, okay? And this is where you can't really, this 100 Kelvin actually should be down there. But my point is, as you increase the temperature, let me kind of just focus on the figures. As you increase the temperatures, you can go from a S for solid to an L for liquid, right? Notice what happens. If you compare those two, all we've done with jacking up the temperature, adding heat to it, is to break some of those bonds. That's cool. Well, we can go from a liquid to a gas if we add more heat to it. Okay. Now notice if we compare the liquid and the gas, we definitely don't have any bonds there. That's awesome. We have no bonds if something's a gas, basically. We have a lot of kinetic energy, kind of shown by those arrows. Okay, so we've increased the temperature, and this is what we've done. Notice that, I don't know if you can make it out, but the red is the oxygen, and the two white ones are hydrogens. So those are cute little water molecules still intact. Notice, now this wouldn't be what we do on Earth, but if we go thousands of degrees Kelvin, or thousands of Kelvin temperature units, notice what's happened here is the water is breaking down into hydrogen and oxygen. So basically, you're jacking up the temperature, and you're kind of jacking with a molecule. Okay, it's no longer a molecule. Basically, all you got are atoms. If you jack up the temperature even more, look what happens. An electron leaves. Okay, the video we looked at about the sun talked about this plasma. That's plasma. Okay, an electron is kicking off. Now, if I go back over here, a little bit ago, I said what causes those lines? The electrons. If something's hot enough where the electrons are stripped away, you're not going to get those lines, basically. Just go ahead and finish that thought. At millions of degrees Kelvin, which would be what we find in the cores of stars, we have even some more interesting things going on. Okay, but that's why it's missing those spectral lines. And these are the ladies, nice little ladies that they are, that actually years ago, I don't know if I have a date, 1800s, years ago, these are the ladies that basically, and I'm amazed that they could do this back then. They actually were looking at a star, and you have to use a telescope, taking the light from the star, passing it through a prism so it makes a rainbow, and then looking for those spectral lines. So these ladies were looking at, this star, this star, this star, this star, this star, and looking for patterns in their spectral lines. So actually, what they started out with A and O, and then they just tried to kind of have some patterns in between there. And then what they did was basically, once they understood what was going on with their spectra, they said, nope, there's only 7 piles. They shouldn't be all that piles. And then they jumbled them with regard to temperature. So O is the hottest and M is the coolest. So I like looking at this guy right here. Doesn't he look kind of creepy / happy? Yeah, I'm just saying. I just think that is cool. All right, so switching gears a little bit. Binary stars, most stars actually have a partner. And I think this is going to be reinforced by the video we're going to watch next week. So some have even more than, we're going to see a picture here in a minute, more than a partner. They have several partners. And this is actually related to one of the things we're going to hit next week is oftentimes stars are kind of all born together. A lot of stars are born at one time. So you figure they're in the vicinity of each other so they can kind of gravitationally hang out. How do we find these pairs of stars? Well, the way we find them kind of gives us what we call 3 different types of binary stars. So there's the visual binary, which just means we find that there's 2 stars visually. Okay? So, there are folks in observational astronomy who just really get a kick out of putting their telescope to binary stars. So here's an example of Sirius A and Sirius B. We're going to talk about these later too, but actually Sirius A is an active star. Sirius A is that bright, like negative 1.4 or something like that. It's a really bright star. Sirius B is its companion. It's a retired star. It's like a white dwarf. So there we go. And you can visually see 2 stars. Here's another example where actually there's Mizar and Alcor. Think Alvin. Let's see. So, of course, you recognize the Big Dipper. And if you look in the handle of the Big Dipper, this star right here, the big one is Mizar, and the rider is Alcor. I think they even call that like a horse and its rider. So, looking at these pair of stars in a telescope gives you this, okay? But, and they call it splitting, actually looking in bumping up your power. Actually, you can take this star, and it's a pair of stars. You can take this star, and it's a pair of stars. So what looks like maybe at first glance as 1 star is actually a quartet. You can split it into 2 pretty easy, and then actually you can split each of those into 2. So I think that's cool. So visual binary. Another one is called a spectroscopic binary. This actually has to do with the Doppler shift. Okay, so what you do with the spectroscopic binary is you can't see you have 2 stars. But what you do is you do a spectrum. So we see kind of a pair of absorption spectra down there. And because they are moving, and I didn't talk about this yet, but the thing, if you have a pair of stars and they're gravitationally hanging out, they actually kind of between those pair of stars is what we call the common center of mass. So between them, and they both kind of dance around that kind of in imaginary place. So if you see them kind of moving, and it would have to be what we call radial motion, you can get a fix on when it's moving towards you and away from you by seeing the shift in the lines like we talked about earlier in class. The last one is something we kind of talked about just recently with planets. Remember we said that you can detect a planet orbiting a star if you do a light meter, okay? And basically as the planet moves behind the star, there's an eclipse occur. If it moves in front of the star, there's a type of eclipse occur. Same thing with a pair of stars. All right. That'd be called that's an eclipsing binary. I don't have a whole lot to add to this slide, okay? But I mentioned that there are people that get excited about turning the telescope to double stars, okay, binary stars. But there's a slight difference, there's a difference between a pair of true binary stars and an optical double. An optical double or optical binary just means that from our point of view, they just kind of line up so they look alike. They're nowhere near each other. They don't have a common center of mass. So, if we see a pair of stars and we can observe them orbiting a common center of mass, we can actually get a handle on their masses by using Newton's laws. So that's where these masses came from. If we let big M sub sun be the mass of our sun, then we have a range of masses out there. Okay, from about 100 solar masses, or 100 times the mass of our sun, to 8% times 8% of the mass of our sun, 0.08 solar masses. And I think here in a minute I'm going to talk, or anyway, why is there an upper limit and a lower limit? Maybe it's coming up. Okay. HR diagrams. Have you ever heard that calculus actually was invented by Newton and like Laplace or something like that? Two people invented calculus at the same time, but Newton got credit. That actually kind of reminds me of this idea in astronomy. Two astrophysicists, Hertzsprung and Russell, from different parts of the world, actually came up with the same idea at the same time. I don't know when it would have been. Maybe late 1800s, early 1900s. But they did what a lot of scientists do. They prepared what's called a scatter plot. So there was data coming in about stars. And what they did, so HR diagrams are important. What they did was, here's my scatter plot. Along the x-axis, they put stellar type. So stellar type. And the 7 stellar type we talked about was O, be a fine guy, kiss me. So O, B, A, F, G, K, M. Those are stellar types. I'm going to go ahead and superimpose. This is going to be an HR diagram. I'm going to go ahead and say hot, or hottest over here. I'm going to say coolest over here. All right. So that was the x-axis. The y-axis, they plotted stellar luminosity. So I'm going to put luminosity along the x-axis. And I'm going to go ahead and do the normal. So like as you go up along the y-axis, it increases luminosity. So that's an HR diagram. And then what they did was to find stars that you knew the luminosity and the stellar type of, and they put them on the diagram. So scientists, when they're trying to figure stuff out, which is what they were trying to figure out stars, they get really excited when they see straight lines. So this is one of the straight lines that they saw. They also saw kind of a cluster of stars up here, and they saw a cluster of stars down here. And they were just kind of just like that. That's kind of bare bones of an HR diagram. We'll talk about why HR diagrams are important. Oh. It went crazy. Okay, so this is an HR diagram. This is exactly what I drew. So along the x-axis, you see stellar types, the O and the M, from hottest to coolest. Along the y-axis, you see luminosity. And each one of those little orbs is a star. Okay, so can you kind of see the straight line they got excited about? And you can see kind of groups of stars above, and then kind of a smaller group down here. And this is just kind of another look at the kind of the creation of an HR diagram. Let me see. Yeah, I think before I move on to the next, let me go ahead and say the significance of this that we'll be talking more about. I don't know if you can read it, but that line of stars right here, this line of stars right here, actually the words are main sequence. So anytime you have an HR diagram and they threw a star and it landed on that line, they call it the main sequence. I'm going to put a little 1 here because that's actually the first stage of a star. Depending upon kind of the nature of the star may move off the main sequence and move in this region, the supergiants and giants, And then actually, when it retires, if it's a certain size, it's going to be down here in the white dwarf range. Speaking of, see Sirius B right down there. Okay, the companion to Sirius A. So that was a 1. This is generally a 2. This would be generally a 3. Again, it's not quite that simple. But that's what we understand about stars, and it started with Hirschsprung and Russell. Stars are sometimes can be given what we call a luminosity class. I don't know what that was trying to tell me. Luminosity class. I guess the only thing to emphasize here is our sun, the important star to us, right? I told you it's a G-type star, and I didn't say this, but the 7 spectral types actually have numbers. The numbers range from 0 to 9. Okay, we just happen to be a G2. And then the spectral class here, I guess would be the most important thing, is a Roman numeral 5. Okay, so actually our sun is a main sequence star, and I think we probably heard that when we watched the video on the sun the other day. So our sun actually lies on that line. Okay. So speaking of course, you see this HR diagram that we looked at a minute ago, and you see the sun? The sun is right there. Okay. So the HR diagram is great at basically showing different stages of a star's life. And we'll talk more about main sequence, but I kind of want to introduce you to the concept of a main sequence star. Main sequence, first stage. It's the longest stage. Okay. Most stars that we get to see are actually in this stage because it's the longest. Okay, so now you see that line on this HR diagram, that's main sequence. The other thing about this line, it might be hard for you to see, I think you can see it, but do you see where up here at the top, that's 60 solar masses, and down here at the bottom, okay, that's actually 0.1 solar masses. So actually we have kind of a cool thing here. We have the most massive, and we have the least massive here. And do you see, I like this HR diagram. They're not all colored like this, but do you see where these are literally blue stars and these are literally red stars? And that's all kind of part of it. Okay, so this is actually kind of just showing you these are main sequence stars, and I can't read the life cycles very good, but this massive star actually is going to have a short life. It's going to have a short main sequence stage. It's going to have an overall short life. This one down here is going to have the longest life. I have some more kind of information along those lines, but it has the longest life, the least massive. Okay. So we talked about main sequence, kind of in the upper, the upper right-hand corner, that's where you get your giants and your supergiants. And the lower left-hand corner is where you get your white dwarfs. Okay. So the video we watched on the sun said something to the effect that the sun is going to basically swell at some point, about 5 billion years from now. And this is what our sun's going to do. We'll talk more about this in the next chapter. But it will move on the HR diagram kind of to the upper, a little bit to the upper right of where it is. Okay. So, I told you that most stars have a companion star, and it works out nice because actually oftentimes a lot of stars can be born under the kind of in what we call the same stellar nursery. We have 2 types of clusters of stars all born about the same time. Oh, it's telling me that I'm running out of power. They sound like monkeys, but they're supposed to be seagulls. So, I don't know. Okay, good, yeah. They sound like monkeys to me. I'm like, what's that monkey chattering? So, if you go to the observatory, a target to turn your telescope to are these two types of clusters of stars. There are open clusters, and the example of an open cluster that your author has here actually are called the Pleiades, or the Seven Sisters. This is associated with the constellation Taurus. Taurus the bull. And I know there's more than 7 there, but they are called the Seven Sisters. And sometimes, can you see a little dipper here? I've heard people, like, they look awesome through binoculars. They don't look great through the telescope, I don't think. But through the binoculars, they almost look like a tiny little dipper.
Yeah, it does.
So, and the other thing, can you see a little bit of, does it look kind of fuzzy? Okay, there's a little bit of nebulosity in this open star cluster. I think that's cool. The other type of cluster is a globular cluster. So they look very different, don't they? Globular, open clusters can take different shapes. Open clusters, you'll say, oh, there's a butterfly cluster. There's all sorts of different names given to these open clusters because they make these different shapes. But globular clusters are all about like a ball, like a spherical sort of thing. Globular clusters tend to be older stars, just like the slide says, located actually in the halo region outside the disk of the galaxy. All right, so taking one last look at kind of what we've talked about. No, let's do it this way. Well, I only have like a few slides, but what I'm going to do on Monday is we're going to knock out these slides and then we're going to watch the video. There should be enough time to do that. So that's what we do. And so you can do the homework if you want to, but it won't be due until Wednesday because that's when we'll officially finish it in lecture. Does that make sense? All right. Very good.